Right, and welcome. So this is the fourth video in our series on quadratics, and this is one where we're going to extend on a little bit further than GCSE now and start looking at something a bit different. And we're going to start looking at what we call the roots of a quadratic equation and something called the discriminant. So what we're going to do is have a look at the roots of the equation, i.e. the solutions, and link them to what that looks like when we start plotting these things in curves. And also using this thing called the discriminant, which is this bit here, which might look familiar to you. You might have seen that somewhere before. I'm not going to give the game away just yet. And look at what that tells us and how that can tell us how many roots a particular equation has got. So here we go. So we're going to look at the connections between the quadratic equations and the quadratic curves, because at GCSE they tend to be studied fairly separately. So what I want to do is bring those two things together, because essentially they're one and the same thing. So the quadratic graph, anything in the form y equals ax squared plus bx plus c, and you've got your values for a, b and c, which are the ones you should be familiar with from your work on quadratic formula. And the most simple version of that is when we've got a is 1, b is 0, c is 0, and that just gives us the curve y equals x squared. We should also know that all quadratics have the same shape, which is either going to be a U shape or the N shape, which is the negative version. And so there you go, there's our y equals x squared curve. And all that's really happening is all the other curves or the equation, what they're doing is either turning it upside down, as in that case it's a negative quadratic, or we've got a positive one where they've been shifted a bit, moved across, moved down, moved up, and then we've got one in the end again, which is a negative again. Just be a bit careful. Let's say this one is negative because it's all about the x squared term. You can see it's a minus x squared there, so that is what makes it negative. But essentially, let's say they're all exactly the same shape curve, just manipulated in some way in this, as I said before, shifted across, up, down, or turned upside down. Now, what we're looking at is the number of roots, and what we mean by that is how many times that the curves cut through the axis, and specifically the x-axis. So if we have a look at the first one, okay, it's not quite cutting through the axis, but it is just touching it and then going away. So we say that that curve there, y equals x squared, has got one root. Clearly, 3 minus x squared, that's going through the x-axis in two places. So that's got two roots. Again, x squared plus 6x plus 5, two roots. This one, I see this one, it's almost like it's floating up in the air. It doesn't go through the x-axis, so it's got no roots. And the final one, again, is just touching the axis, not going through it, and then going away again. So that has just got the one root. So depending on where these curves are, depending on which way up they are, has an impact on how many roots they've got. So we're just going to have a look in a bit more detail about what causes that and strengthen our understanding of why that happens and how we can determine, without having to draw the graphs, how many roots or solutions we're going to get to an equation. Right, so we know that where a curve cuts the x-axis, you've got the y-coordinate is 0. What that means is, if we're going to take an equation, all we've got to do is plug in y equals 0 and then solve it, and that will find us the root. So for that curve there, which is y equals x squared plus 6x plus 5, I've just got to replace the y, letter y, with a 0. So when y equals 0, we've got that. And now we're straight back to our standard structure for how we go about solving an equation. And we know that equation can be solved by factorising. So we've got x plus 5, x plus 1. That gives me two solutions, minus 5, minus 1. And so that would be minus 5 there. That would be minus 1 there. Now, we've solved it simply by factorising, but I am also going to do this using quadratic formula. And we'll see the reason for this in just a second. So there we go. There it is with quadratic formula. So we've got x equals minus 6 plus or minus root 16 over 2, which gives me exactly the same values. If we have a look at our next curve, which is the one that was kind of floating up in the air, the one with the, from our diagram we can see it's got no roots. We've got to solve that equation. And we can see straight away it's not going to factorise. It looked like it might to begin with, but we've got to have the 3 and the 1 have got to be the same sign. So it's got to be plus 3 and plus 1, which would give us plus 4x, or minus 3 minus 1 giving us minus 4x. It won't give us the minus 2x that we need in the middle. It won't factorize, so I say, okay, well, if it won't factorize, let's see if we can do it using a formula. There we go, plug in the values, and if you put that into your calculator will have a bit of a strop. It'll say math error, and it's saying math error because we've got that minus 8 underneath the square root, because you cannot have the square root of a negative number. So straight away, we can see that what's happening under the square root is going to be, or is going to determine, to an extent, how many roots this equation has got. You'll notice this is why I did it over here. We see we've got a positive number of the square root. So from here, that's going to be 4. So we're going to have minus 6 plus 4, or minus 6 minus 4 over 2, generates our two solutions. Here, because we've got a minus under there, we're not going to get any solutions at all. There are no values of x that will solve the equation. So, no solution, therefore no roots. What that means is, if we've got an equation with two roots, that's the one we had from the previous slide. We've got two solutions, and that's happened because we've got a value underneath our square root there, 16. Here, we've got one root. That was our 8x minus x squared minus 16. See, it's just got the one root. It's just touching the x-axis there. If we have a look what would happen if we did this one using quadratic formula, we'd end up with that. Now, what's happening here is I've got a value underneath my square root that's a 0, so I've effectively got minus 8 plus or minus 0, all divided by minus 2. So what's happening is effectively got minus 8 divided by minus 2. So that's given me two solutions. Both of them are x equals 4. So we say, technically speaking, it's got one root, but it's repeated because we've got one root and it's happening in the same place. And then finally, again from our previous slide, we saw that that one has got no roots because of the minus underneath there. And you can see it's the values that's underneath the square root that's telling us precisely how many roots each curve or each equation is going to have. So we can say that our first equation has got two distinct and real roots, and the bit under the square root, which is b squared minus 4ac, that bit has got to be bigger than 0, so we've got a positive value underneath our square root. As I said before, we've got one repeated root here, because we've got a 0 underneath our square root, so we know that b squared minus 4ac has got to equal 0. And then finally, we've got no real roots because b squared minus 4ac is less than 0. And it's that b squared minus 4ac, that bit underneath the square root in the quadratic formula, that is the thing that's telling us how many roots an equation has got. And that thing there is called the discriminant. I've put that in a massive, great big yellow box because, again, you're going to be tested on this time and time again, and you're going to get asked questions about, can you work out the value of b squared minus 4ac, and once you've got that value, what does that tell you about the number of solutions that an equation has got? So let's have a look at exactly that kind of a question. So in these examples, we're not being asked to actually solve the equations. What we're being asked to do is determine how many solutions there would be to these equations if we did solve them. So what we're going to do is calculate the value of the discriminant, and that's going to tell us how many solutions each equation has got. So first one, we've got x squared plus 3x plus 5. We need b squared minus 4ac. So b is going to be 3, a is going to be 1, and c is going to be 5. So b squared minus 4ac is 3 squared minus 4 times 1 times 5. So that gives us a value of minus 11. And what that means is, because it's a negative, that would be the bit underneath the square root. It would mean there'd be no real solution or no real roots. In part B, we've got that equation. Now, I've said earlier that anytime you solve a quadratic equation, you've got to have it equal to 0. Exactly the same principle applies here. Before we can start doing the discriminant, we've got to get our equation equal to 0. So that means I'm going to have to do some multiplying out and some rearranging. So we've got 9x squared minus 12x plus 4 is the multiplied out version of 3x minus 2 all squared. Do a bit of rearranging. Now I've got it equal to 0, so now I can start working with the discriminant. And again, I'm going to make sure that I write it down so I can show in the exam I know exactly what I'm doing. b squared minus 4ac. So now we've got minus 8 squared minus 4 times 9 times minus 1, which is 64, which is minus 8 squared. And then because we've got c as being a negative, so we've got minus 4 times 9 times minus 1, so that makes that a plus. So the discriminant is 100, and so what that tells us straight away is that's bigger than 0, so we've got 2 real roots. Third example, again, I'm going to make that equal to 0. So move over the 4x, move over the minus 1. b squared minus 4ac is going to be minus 14 squared minus 4 times by 1 times by 49. So that's 196 minus 196, which equals 0. And if the discriminant equals 0, that means I've got 1 repeated root. Okay, so there we weren't actually solving, we were just looking at the discriminant and determining how many solutions each equation would have. On we go. Now, you see these kind of questions quite frequently appearing on exam papers. So it says, find the values of k for which each equation has a certain number of roots. So here we go with the first one. So we've got x squared plus 6x plus k equals 0. So that k there just represents a number. And we'll say, okay, well, what would that number be in order to have distinct real roots? Well, that means that b squared minus 4ac has got to be bigger than 0. So that means I've got b squared, which is 6, minus 4 times 1 times k. So obviously this thing here is going to be c in b squared minus 4ac. So what we've got now is a simple inequality to solve. And again, just being a little bit careful, because you've got a minus in there, so you're going to have to think about carefully how you deal with your inequalities. I prefer to take the 4k over to that side so it's no longer a minus. Whichever way around you do it, you end up with k has got to be less than 9. So in order for this equation to have real or 2 distinct real roots, we've got to have a value of k that is smaller than 9. Okay, in the next one we've got again this constant k, and it's appearing as the x squared coefficient. It's appearing as part of b as well, and it's also appearing as c here. So we've got a equals k, b equals 2k, and c equals k minus 5. And because it's got no real roots, we need b squared minus 4ac to be less than 0. So plug in everything that we've got. So there's our b squared, and again making sure I've got brackets because I want 2k all squared, so I've got to think very carefully about that, minus 4 times k squared minus 5. So we've got 4k squared, that's my 2k times 2k, minus 4k lots of k minus 5. Multiply out the brackets, and you'll notice, fortunately in this particular case, the k squared parts cancel out against each other, so I'm left with that. So that's telling me in order to have no real roots, the value of k has got to be less than 0. If the value of k was equal to or bigger than 0, then I would be able to get solutions to that equation. And then finally, the third one, again, we've got k's popping up all over the place in here. So here we go. Repeated roots, so that means that b squared minus 4ac has got to be equal to 0, so it's got to be exactly a particular value. Notice here I've got b squared. Now we've got to be really, really careful here. The number of times students make this mistake when you've got actually this b is a negative 3k minus 1, so we've got to make sure we're including the minus there. And I've got brackets around 3k minus 1 and brackets around the squared bit as well, because I've got to remember to square that negative. It's an amazing number of times you see students writing it down correctly and then not squaring that minus sign. Minus times a minus makes a plus. So what we've got is 3k minus 1 all squared, which gives us this expression here, 9k squared minus 6k plus 1. Over here, I've got minus 12 plus 12k, which is going to come from multiplying out this bracket. Do a bit of tidying up, and there we go. We've ended up now. We started out with a quadratic equation in terms of x, but to decide what values of k give us repeated roots, we've ended up with a quadratic equation in terms of k. So now we've got to solve that quadratic equation. I'm going to have a look at that and think, well, can I factorize it? There's nothing immediately obvious going on there, so I'm going to use quadratic formulas to do it. So k equals minus b plus or minus squared b squared minus 4ac all over 2a. And that gives me that value of k. Looks horrible and messy, but basically what we're saying is if k was this value here, minus 1 plus 2 root 3 over 3, or minus 1 minus 2 root 3 over 3, those are the two particular values that would mean that when I put them in here, I would end up with a quadratic equation that had repeated roots.